Current theoretical models frequently assume that coherent physical structures can be erected from an absolute void using ungrounded axioms. This assumption, known as ex nihilo construction, serves as the foundational starting point for both modern physics and mathematics. We see this in Zermelo-Fraenkel set theory, the standard axiomatic framework for math, which posits the existence of the empty set. It appears again in the standard model of particle physics, which assumes the existence of frictionless point particles. Both systems build complex order from a vacuum that lacks defined geometric necessities. These frameworks essentially begin in the middle of the story, smuggling structure into the void before formal logical operations have actually commenced. Because these initial structures are posited without adequately defined bounding constraints, the resulting systems are inherently ad hoc. Building reality from a frictionless zero creates a fragile architecture. By ignoring the origins of its own axioms, the field is navigating a systemic epistemological rupture, where foundations are vulnerable to boundary failures. This failure is exposed mathematically in the domain of symplectic geometry and contact topology. Symplectic geometry is a branch of mathematics that studies the geometric structures of phase spaces in physical systems. Within this domain, researchers analyze the behavior of holomorphic disks by constructing a moduli space. A moduli space is a geometric space where each individual point represents a different possible configuration of a mathematical object. The crisis emerges through the principle of surjective invariance. This is a threshold reached when a specific evaluation map fails to be surjective, meaning it cannot cover the entirety of the target space at its boundary. The consequences are absolute. Because the map is not surjective, its degree is zero, which dictates that the moduli space cannot achieve Gromov compactness. Gromov compactness is a topological condition that allows a sequence of curves to converge into a closed, stable limit. This severe lack of compactness causes the space to leak toward infinity, rendering it impossible to seal analytically. Standard topological paradigms treat this non-compactness as a terminal divergence, leaving the mathematical description of reality fundamentally uncontained at its extreme limits. An independent theoretical research nexus in Vancouver, British Columbia, has proposed a new ontological framework to address this rupture. The theory of infinity, or TOI framework, treats non-compacted divergence as a diagnostic signal rather than a mathematical failure. This framework defines the unsealable boundary as not infinity, an active generative primitive that marks the threshold where new mathematical structure is born. The TOI engine shifts the focus toward ex totalitate formation, the topological extraction of a bounded context from an all-containing, indeterminate totality. To bridge the continuous and the discrete, the framework utilizes the generative triad, a sequence of operations that forces the infinite continuum to yield a closed, theorem-bearing context called the golden set. In this paradigm, infinity acts as the parent substrate from which all physical limits and geometric constraints derive their exact shape. The infinite plenum possesses an inherent fundamental asymmetry known as the primordial twist. This twist features two opposing geometric channels, the acute and grave orientations, corresponding mathematically to left and right-handed spinor states. This asymmetry creates a lopsided reality, unable to form a stable golden set. Stability requires a spinatorial twist collapse to perfectly neutralize their directional force. This collapse results in parity-even closure, a state where the opposing spinors perfectly balance to zero, neutralizing the primordial twist. A sound cosmological structure is the mathematical byproduct of crushing these asymmetric tensions into a state of perfect parity. To test the resilience of this structure, we must attempt to embed discrete algebraic recurrences into the continuous golden set manifold. This process generates measurable mathematical error gaps at the boundary between the smooth manifold and the discrete sequence. These gaps align with John Nash's theories on geometric friction, which he used to explain cosmological redshift through gravitational fluctuations in a wrinkled metric tensor. A metric tensor is a function that defines the distance between points in a geometric space. In functional analysis, forcing rigid constraints onto a smooth manifold causes a loss of derivatives. Functional analysis is the study of spaces of functions. This interaction mathematically shreds the regularity of the function. Sequence algorithms experience this Nash-Moser topological friction, losing the smoothness required for the sequence to stabilize before it can reach convergence. These boundary errors represent the physical manifestation of topological friction affecting the fabric of continuous space. The law of topological mass exchange governs how this friction is managed, ensuring that conservation laws are maintained across the boundary. The winding genesis operator applies an alternating sign to a polynomial, trapping topological tension. The system toggles states, exchanging geometric mass. We see the heavy mass value, 0.7373, swap between the real root and the complex squared magnitude. This exchange constitutes mass being sequestered and moved across phase space, keeping the topological total of the system universally conserved. The Dyadic lineage ledger acts as the cybernetic protocol for this process, requiring that every boundary crossing is logged with its measured and typed friction. By capturing chaotic friction within a precise ledger, the framework demonstrates that mathematical anomalies at the boundary are the conserved structural blueprint of the absolute.